we move on to the presentation of John Furbish, which is focused on statistical relations among quantities in sediment transport, and then a discussion. Please, John.
Thank you very much for this opportunity. Speaking of Mark Schmeckley, we're watching a simulation of bedload transport that Mark Schmeckley produced. It is a large eddy simulation for the turbulent flow above the bed. The motion of the particles is a discrete element method, as Kimberly described previously. These two are fully coupled in momentum, that is to say the particles and the fluid are continuously exchanging momentum back and forth. I like this video particularly because it nicely shows or nicely offers a cartoon of the very patchy motion of this and start and stop behavior of the particles. And one of the things that I would like to point out at the outset here is that the motion of the active particles are at low concentration. They are effectively representing a rarefied condition, and that point will come up again momentarily. I'll show you the real thing as well. Let me start with the points that I would like, the principal points that I would like to make about the talk, and I'll return to these at the end. I'm focusing on the entrainment forms of the flux and the Exner equation, particularly because they provide a very nice probabilistic framework for examining details of particle motions, the flux, without assuming at the outset of a continuum behavior. The central elements of this formulation, as you perhaps know, involve the entrainment rate and the joint probability distribution of the particle hop distances measured start to stop and the associated travel times. When we can express this in a convolution form, it effectively has the form of a master equation, which is a general probabilistic formulation that is both non-local and scale independent, and those two properties are very nice. We can approximate this as a Fokker-Planck-like equation, which possesses advective and diffusive parts, and indeed the idea of advection and diffusion fundamentally are probabilistic constructs. The diffusive term is actually an approximation of the non-local behavior. A theory and experiment suggests that the expected hop distance goes as the square of the travel time, and that's dimensionally sound. There is a stochastic term that is involved. Theory and experiment suggests that the travel times are exponentially distributed, which, because of the covariance between these two quantities, requires most likely that the hop distances are a Weibull distribution. And finally, I want to comment at the very end about the idea that when we write a continuous differential equation, the Exner equation, I would suggest that what we're actually doing is describing a statistically expected behavior in the same way that we think about, for example, the logarithmic velocity law. That is an expected behavior as opposed to something that happens at any given instant in an actual realization. Okay, very briefly, the motivation here. Of course, the Exner equation is a foundation of what we do with gravel bed rivers. There are two versions, a divergence form, the entrainment form, which I will focus on. Both can be expressed in the probabilistic form of a master equation. That framework then, of course, allows us to think about the details of particle motions, including the behavior of tracer particles, which, of course, is something that is emerging of increasing interest, including sediment-borne substances. And then, of course, as you perhaps know, folks are beginning to think about how changes in bed topography influence tracer motions. In appealing to a statistical mechanics perspective, and in particular if we are thinking about the possibility of rarefied conditions, particle mechanics generally suggests that we have two choices. Probably there are more, but the rule of thumb is either we must go to discrete particle models or we must appeal to methods of statistical mechanics. And so we're approaching this from the perspective of statistical mechanics. That in turn requires us to think about the idea of a Gibbs-like ensemble for sediment systems. And in turn, the idea that when we describe, say, the distribution of particle velocities, as an example, importantly, that needs to be recognized as a formal ensemble distribution, where I wish to point out that I am not talking about an ensemble of particles, I'm talking about an ensemble of systems, which I'll show you momentarily. Okay, starting off then, the idea of a sediment, a Gibbs-like sediment ensemble. Let's start with Gibbs, who effectively introduced and defined in one sentence the idea of an ensemble of systems, in which he asks us to imagine a great number of independent but identical systems in nature, differing only in their configuration with respect to velocity and configuration. Now he's focused on configuration of particles and their velocities. As Cattell points out, what Gibbs is effectively asking us to do is to replace time averaging with ensemble averaging, which of course is leads to the problem of the question of ergodicity, which is key to proper interpretation of experimental measurements. And finally, I want to emphasize, as Cattell points out, the idea of an ensemble is very different in statistical mechanics from what we normally refer to as an ensemble. To outline the idea of what I mean here, here very briefly is our experimental conditions. That's Mark Schmeckley. We're at Arizona State University. 2 cameras. We have a laser sheet that allows, horizontal laser sheet that allows us to do high-speed imagery both of the particles and the near-bed fluid. Here's the real thing, and now I want to describe the idea of an ensemble. The frame rate here is 250 frames per second. I want you to imagine an individual frame. There are active particles during that frame. The particles have a very specific distribution of velocities. We can calculate a very concise average velocity. Those average velocities likely are correlated from one frame to the next. Here's what I want us to do. Imagine taking all of those frames and randomizing them such that we lose the serial correlation. Effectively, each frame now represents a nominally independent but otherwise identical system. What we have now defined is in effect a Gibbs-like ensemble. If we take the average of all of the average velocities, we have defined an ensemble average formally. Now, equally important, what we're after is the expected values of the velocities as determined by the ensemble of independent systems. That represents the ensemble distribution of velocities. Okay, what do those look like? This, for example, represents a set of measurements, just focusing on the first couple of points. This is the number of particles in motion during each frame. Notice the fluctuations, the frame average streamwise velocity, and so on. Now, without going into the details, we do have to appeal to ergodicity to suggest that the distributions associated with these are indeed ensemble quantities, and I want to stress that at each instant, in effect, what we are doing is drawing a sample from an underlying ensemble distribution. Here they are, for example, the streamwise velocities are exponential in form. Cross-stream velocities have a Laplace-like structure. Streamwise accelerations also are Laplace. These are just examples. Let me turn briefly to the idea of rarefied conditions. We can define, using the number activity, the number per unit area, we can define a characteristic length scale, which is analogous to the mean free path. We can define a characteristic length scale. If you are a numericist, you may think of this as the grid size. We appealed to the definition of the Knudsen number, which is the mean free path over a characteristic length scale. The continuum approximation is satisfied if the Knudsen number is quite small. Appealing to experiments from Roseberry, but we've gone through a whole bunch of other measurements for these number activities, which are quite typical and are similar to the videos that Kimberly previously showed. These are the length scales over which a continuum approximation is satisfied. Think of it another way. That's the scale for this number activity. That's the scale over which you would use a grid cell, a numerical grid cell, to use a continuum-like approximation. Okay. Very briefly then, the divergence form of the Exner equation, the rate of change of bed elevation, the simplest form of the entrainment form is the difference between entrainment and deposition, where importantly the joint distribution of hop distances and travel times takes center stage. We can take the deposition rate, rewrite it in terms of the entrainment rate, where what I want to stress is that at any particular position x, the first integral is describing non-local conditions in which it is looking upstream and describing the contribution from all positions upstream to those at x. Likewise, we do the same thing with respect to time. This is what we just looked at. A change of variables that I'll not go through with leads us to what expanding to second order, that is this quantity, leads to a Fokker-Planck-like equation, and I want to stress something rather importantly. The flux that goes with that, this is the advective part, this is the diffusive part. That diffusive part is actually an approximation of the non-local behavior contained in this type of formulation. We can calculate a length scale to show that this diffusive flux is quite good so long as the average hop distance is significantly less than that characteristic length scale. In the case of uniform transport, where this term vanishes, this reduces to Einstein's definition of the flux. Let's turn briefly then to this relationship between the two. We predict experiments, observations, and basic theory suggest a squared relationship between them. I just want to point out that from travel time is an integrated quantity, so we can also think about particle age, that is, the time from the beginning of motion of the particle, that's its age, and then when it stops, that's its travel time. But travel age is in fact an instantaneous quantity. We can write the probability distribution of particle age. It satisfies an advection equation where particles age at rate 1, that is the advective velocity. That is, you age per unit time at a rate of 1. Under steady state conditions, or if you wish statistical equilibrium conditions, this distribution then goes to the ensemble distributions. Okay. There are a couple of arguments to suggest that the rate at which particles, once they are entrained, become disentrained ought to be a probabilistic fixed quantity. And indeed, one can define the mean travel time, which is nothing more than the mean residence time that particles spend in motion, that is, in the reservoir above the bed. And that's nicely argued by Davy and Legge. In any case, what we the suggestion is then that the travel time ought to be exponentially distributed. Those are the data consistent with previous measurements as well. This is straight out of an introductory probability text. If we neglect the stochastic term momentarily and we assume that ages are exponentially distributed, that leads directly to the idea that the travel distances ought to be a Weibull distribution with shape factor equal to 1/2. What we actually find is a Weibull distribution with shape factor slightly greater than 1/2, which is probably associated with the fact that we have neglected the stochastic part in the transformation. And finally, let me say something about the idea of the use of continuous functions. Remember, these are now ensemble or expected distributions. That is the distribution of travel distance and hop distance, travel distance and travel time. At any given instant in a real realization, that is not what is happening. At any given instant, we have a sample being drawn, that is a sample of particle motions being drawn from the underlying ensemble distribution. So we can define the actual thing that happens at an instant. Then we can define the actual as being equal to the ensemble plus a deviation. We describe the entrainment rate, the actual entrainment rate as being the ensemble expected value plus a deviation. Go through the entire mathematical rigmarole that I glossed over previously to obtain the, for example, Fokker-Planck-like equation, which looks identical to what we had before, but with now a stochastic term. This applies to the evolution of the bed of the ensemble conditions. That is, this is describing the expected evolution of the stream bed, and at any given realization, that noise term is a nasty thing that we cannot integrate. The reason we can't integrate is because these functions are not necessarily continuous functions, where the ensemble functions are continuously differentiable. So there's a noise term, and I think a principal challenge will be to, in fact, clarify what the effect of that additional noise under a particular realization has to do when we approximate the behavior of, say, a stream bed using a continuously differentiable Exner equation. Let me point out, I hope that we hang on to continuous functions. I'm not suggesting that we abandon them. What I am suggesting is that I hope that we will gain a deeper understanding of what they are actually representing. Thank you.
Thank you, John. We are perfectly on time with respect to the to our timetable, so I open the discussion. In principle, I have a piece of paper saying that Philippe Frey wants to ask questions to all papers. I don't know why. So if Philippe wants to start, well, otherwise we just raise hands. I don't see Philippe, so I don't know. Okay, Christian.
Yeah, Cristian Escauriaza from the Universidad Católica in Chile. Both talks very interesting. I had one question for Kimberly, another for David Furbish. Kimberly? If you have run the simulations longer, do you think you should have started seeing armoring in the simulations of your the discrete element method? Because you saw that initially you had an increase on the transport, but then you should think it should decrease if larger particles get exposed and the smaller particles.
Yes, thanks for your question. Probably went through that too quickly, but you're absolutely right. As the simulation progresses, we drop the finer particles on the bed. The transport rate immediately is very high, and it's at the highest it is. And then armoring and sediment transport, sometimes it's because the fines go away, but of course in our system it doesn't because of the periodic boundary conditions. But the large particles do work their way to the top. So over time, a few different things change, and one is the relative position of the different particles in the bed. Large particles go up, the small particles go down, so you get that armoring effect. Mm-hmm. The other thing that changes is the transport rate gradually changes. And so I showed a parametric plot of essentially the concentration of the particles in transport. That was on the horizontal axis, and the vertical axis was the horizontal axis was the concentration of particles. The vertical axis was the transport rate total. And as the coarser particles increased in concentration, the transport rate went down. So it's exactly what you said. So yes, we get armoring, and yes, with armoring, the total transport rate drops.
Excellent. Thank you. And David, can you explain a little bit more about the length scale? Because I understand that the diffusive term is a good representation when your scales are much larger than the length scales of a hope, because in that case you have correlation, so probably a purely diffusive or Gaussian type of is not a good approximation. What is the length scale that you define that I
probably can get to it.
That one, yeah. Can
Okay.
you explain a little bit more about that length scale and how you go? Thank you.
This is straight out of any fluid mechanics type text in which you simply are taking the derivative of a quantity with respect to a coordinate position, and in effect using that to define a length scale. So what I'm actually doing is taking that entire quantity and simply taking its derivative with respect to for example. Yes. So basically what this is telling us, this is a measure of the distance over which those quantities are changing. So if this is very, very, very long, it means that they're not changing, right? Okay. It means it's uniform. And all that we're saying is, so long as the distance is shorter than that characteristic distance over which something is changing, then that's a very good approximation. Yes.
Okay. Okay, let's start from that side and then we come slowly to this side. We have plenty of time, I think.
Yeah, I have a question about...
Introduce yourself.
I'm Jeremy Vendetti from Simon Fraser University. So I have a question again about the prototype for these, for the theory and for the rheological model that you use. So it seems to me like a lot of flume experiments are done at really, really high transport stages, but then when I go out to a gravel bed river, even at bank full flows, I see like 5 or 6 particles moving, and so that I wonder how that affects your rheological model if you slow down the number of particles moving. And then, of course, in the theory, I think that the distributions become not continuous anymore, but I'm not sure of that. Could you both address that?
Sure. So the rheological model from the granular physics, it goes all the way until the particles are almost not moving, but suddenly when we get to the sort of what the granular physics types like to call jamming transition, then suddenly you see a divergence of behavior. And that's partly because non-local effects start to take over. So this is very relevant. And so I would say that probably the mu-I rheology, it's there, but then there's another, the way that people are starting to address this, there's another factor involved that brings in the non-local effects. And the closer to static, the quasi-static state is, the more important that term becomes. And if you want a name of someone who's published a sort of a little bit of a flurry of of work in the granular physics community. Ken Cameron, K-A-M-R-I-N, is addressed that. And so, so it'd be interesting. We have not gone back and tried to see how that applies to a bimodal system, and partly because no one's done it for mixtures yet. But right, it would break down into that limit. Okay.
Going to small transport rates, you are spot on. Those distributions are not continuous. And in fact, that is precisely why I am suggesting that in thinking about this as a statistical mechanics problem, what you must define, in fact, is the ensemble distribution, which fundamentally is a continuously differentiable function. And what is happening in nature is exactly what you described, is the actual thing, which probably is not continuous at low transport rates, and which is why I'm not going to try to integrate those, because those likely are not continuous functions. Whereas the part that led to this, I am integrating continuous functions, the ensembled quantities. Does that clarify? Incidentally, Giri and Shimizu actually, in roughly 10 years ago, set this problem up. They don't do an LES, they do a fluid flow model, but they're actually solving for the motions of the particles, that is the hop distances, and in effect they actually produce ripples, okay, due to the randomness of the behavior of the particles, and they do in fact have feedbacks that contribute to that.
Thank you. I saw, yeah, and then we come to you.
Bill Dietrich, UC Berkeley, and we seem to get one each to the speakers. Speaker number one, behind black shirt. John, this is, I want to get one thing. This is fabulous what you're doing. This is a description of sort of the kinematics of things, as I understand it, and as compared to why there's distransmission and what sets the distribution function of the system. Are you going to tell us how to do that part of the problem so I know when to expect erosion and deposition?
Eventually. You are correct, Bill. This so far is actually trying to get the kinematics correct. And I would argue that that's absolutely key in this problem. We have been beating ourselves up for a very long time. And in fact, I think we have been neglecting some of the important basic descriptions of particle motions before we then move on to a more dynamical expression. Now, that said, I don't want to at all detract from what are in effect very wonderful, clear attempts to do the dynamics. For example, when we talk about the mean hop distance, one can make arguments that ought to scale, for example, with that is, that expression ought to, for example, scale with some characteristic quantity of the flow, for example, shear velocity and so on. So there are dynamical-like arguments that have indeed begun to inform the parameters of this type of formulation. But I'm hoping we will collectively get there.
And then, Kimberly, my question for you is, there's one small detail that may sort of get to Jeremy's question too. You had as a reference velocity a log profile through the system, and you had it penetrate in some distance into what you might call the bedload layer. When the system aggrades, does that reference velocity go up or does it stay fixed? Because that has a very profound effect on internal mobility.
It moves up. So each time step, I didn't go into sort of the flow chart for how we do the simulations, but each time step we reevaluate where the top of the bed surface is, and we define that based on what the particle velocities are compared with what our expression for what the velocity should be at the bed surface.
If that's the case, then I'm still puzzled how you're getting such deep mobility. What it looks like is you range your particles in, and you had multiple grain depth motion at the scale of the larger particles. Mm-hmm. And that if you're not on a steep slope, then what's your source of causing those particles to move other than a flow? And if it's a flow, why aren't you down at already to zero velocity?
I think it's a very interesting question, and it gets to an intuition difference between people working with spherical particles and people working with aspherical particles, because not too much asphericity and partly bumpiness of the particles can lock up the particles and cause dramatic differences in their response to shear stresses. So I think the reason why we're getting what seems to be enormous steps into the flow, which is not really that enormous to a granular flow person because the shear stress doesn't penetrate that deep in, is because we're doing spherical particle simulations and these kind of simple things. It's easy enough to incorporate, so I don't want to disparage all my colleagues who do much more complex DEM simulations. You can perform DEM simulations with rougher particles relatively simply, but they take longer, and so we did the simplest ones. I think if you did slight asphericities that way, you would see something a lot closer to what you're describing, and that is movement only along the top bed. That being said, I think that we still are capturing what we want to capture in the relative particle size. It just is moving more particles than we think that it should.
Right, but there's that term you used, the third door, was a granular physics or something effect. And to put an exact identification of what that is in your granular model that's causing the finer grain size to cause mobility, it is what? The other two, the literature is full of hiding effects. So you're saying there's a granular effect. We witness you putting particles in. So say exactly what that is.
Right.
That's the granular effect.
So if we go back to the mu-I rheology that I had a sort of dash through, one of the things that's just been looked at only recently is how that applies to particle mixtures and how you can just throw in an average particle size even if that's not represented in the mixture. So you have this inertial number that's dependent on average particle size that governs everything. Okay, why does that depend on average particle size? And that's the granular effect. So it's like getting from the mu to the I to the average particle size. What we have found is that, and so what we believe is behind that, is that those parameters move around with a ratio of collisional time scales that has to do with the duration of particles in contact as well as the time between collisions. So the ratio of those two time scales is the particle scale effect that then kind of propagates down into the mu-I rheology, it turns out.
Okay, that's the pure granular effect.
That's the granular effect. Yeah, thanks for that question.
Yes, please.
Paul Carling, University of Southampton. This is a question for Kimberly. I wondered if you could explain a little bit more why you're applying the concept of wash load and the Rouse number to the infiltration problem. I mean, the Rouse number, if it applies at all, the concept of wash load, if it applies at all, only applies to the end of the finest end of the grain size distribution. And the Rouse number does not necessarily control the infiltration rate.
I wasn't meaning to apply it to the infiltration, just looking at what coincides. So when you have the finest particles, it infiltrates all the way down to the bottom. And that's probably closer to related to the ratio of particle sizes, because it's the fine particle size compared with the space between particles. The Rouse number seems to be capturing when we transition to wash load, which may not be directly related to the transition between something closer to sand camping and something closer to complete fines infiltration. So sorry if I confused those two.
No, that's okay, and I think it needs a little bit more careful consideration, because material in suspension is not necessarily wash load, and I'm not sure if I believe in the concept of wash load anyway. But you can run suspended sediment over a porous bed at very high Rouse numbers, and you just get infiltration because the particles, although they're in suspension, they come in contact with the bed and they become entrapped. And the main driver is the concentration in suspension.
Mm-hmm. Right. So one of the questions that we were very curious about is this phenomenology as to whether or not the fine particles are affecting the transport rate. And when transport rate and maybe other measures of the mobility of the bed, like the bed slope. So in terms of the stream restoration, it was the bed slope. So in that sense, it's a real effect that you add a bunch of fine particles and you don't get a reduction in slope, even though they're finer than the ones that were causing reduction all along. So I'd say maybe I believe in wash load more strongly than you do, but with more limited definitions than it might be applied, like wash load applied to the morphology of the river or something like that. And that was what we were mostly trying to look at, and I was trying to tie in other observations to that. But it's an interesting point. Maybe we can talk about it more later. Thanks.
Hello, Philippe Frey from Irstia and University Grenoble. I have, I think, a question for both of you. Kimberly, you mentioned the fact that you have aggradation or degradation depending on the grain size ratio. Recent experiments we made with Ashley Dodil in the room. Also, it also depends of the ratio of the fine particles over the total supplied. But when we looked at some videos, one assumption I have, it's a mere assumption, is that you have degradation when you have less, how can I say, disentrainment possibility, or less disentrainment sites. So I was wondering, first question for Kimberly, with discrete element models, with coupled discrete element models, can you actually have a nice idea if you look at the velocity or acceleration or local configuration? Could you actually try to have a final look? Is this disentrainment possibility? And for John, I have a question about in the stochastic framework. There are considerations about entrainment, about time, start and stop time. But what about, how is it exactly modeled, this entrainment? How does it come in play into the master equation? So basically, this entrainment, that's the subject of my question. Thanks.
So I'm going to ask a quick question of clarification. Are you saying that in your experiments, you've looked very closely at what the particles are doing when you get sort of mobilization or not, aggradation or degradation, and you're finding a big correlation between a change in disentrainment rates or something like that? Is that sort of the observation that you're tying to this?
I'm just saying, at this stage, it's just qualitative. It seems that over the transition, when you have the initial slope, and then when it degrades, particles are entrained, and then it is degrading because particles cannot stop anymore. Okay, because for whatever reason, because the surface is more or less smoothing, because from a granular point of view, there's less and less sites for particles to stop. I don't know exactly, but yeah.
Yes, I think that a more sophisticated representation of the fluid would help show whether that there's an asymmetry between the entrainment and disentrainment as you get the sort of geometric smoothing. I think that would be helpful, and maybe turning it on and turning that effect on and off in the simulations would be helpful too. Yeah, thanks for the suggestion.
With regard to particle entrainment, first, it's interesting that we have historically given a lot of attention to the initial motion problem, if you wish. But we've given very little or limited attention to the disentrainment process. And I just wanted to start off by pointing out that I think that's a very exciting idea that needs to be pursued to, in fact, add the dynamics to the entrainment and disentrainment, which then sets the travel times and the associated hop distances. We're here talking about gravel bed rivers, but if in fact we were talking about the process of particle rain splash, then I would actually be able to answer both your question and Bill Dietrich's previous question, in that the entrainment rate, the physics of that have been worked out quite nicely. And indeed, the travel distance and its variance, also the physics of that have been worked out quite nicely. There are some details that we still need to get at. But in the river problem, of course, there is turbulence, and as you know, it is a Millennium Prize problem to understand turbulence, and that's wherein the rub lies. There are several folks who have, from a spatial temporal average point of view, suggested that entrainment rate, for example, scales with, again, shear velocity, for example. And I think in a very basic way, that's a reasonable first approximation. Other folks have looked at it from an energetics point of view. I'm aware of at least one paper about 5 years ago which suggested one could think about entrainment rate in a quasi-statistical mechanics sort of way, looking at turbulence energy, for example. I know folks have, I can't give you details here, folks have looked at, for example, turbulence kinetic energy as a way of getting at entrainment rate. But I think one of the cool and interesting parts is the disentrainment rate.
Down here? First line. Oh, thanks.
Gordon Grant, U.S. Forest Service, also Oregon State University. This is for Kimberly, and it's sort of a crazy idea that I'm sure wouldn't work. But, as you tried to isolate the effect of the particle interaction and suppress the turbulent component, I wondered, did you consider playing around with fluids of different viscosities as a means of changing that, and that I don't know what, some light oils or something like that, as a way of disentangling more precisely the effect that you're trying to get at?
That's a great question. I love it. Yes, but so far not with sediment transport. I've been more in looking at debris flows, trying to play with that a little bit, but I hadn't. And I'm thinking you're talking about experimentally rather than right. No, that's a great idea. I think it would be fun. Is that so? It seems like a yes or no, right? So the way that one of the details that I left out in the simulation that I think would also be good to incorporate that into the simulation is the manner in which viscosity of the fluid mediates the interparticle interactions, and that's another way that I could simultaneously look at it experimentally in simulation. So thanks for that suggestion. A lot of fun.
Up there, question?
Hi, Michael Attal from the University of Edinburgh. I've got a short question for John. So how easily would it be to integrate the grain size effect in your framework? Sorry.
I've lost sleep over that question. I think in principle, the kinematics of it are very straightforward. It's bookkeeping. One may think of the master equation as the ultimate bookkeeping ledger. It's really a statement of conservation of probability. That's all it is. And so from a kinematic point of view, the mixed problem, I think, is straightforward. It's the dynamics part that is, of course, tough. And I was just going to add that the video that I showed that Mark Schmeckley has done, he's done mixed particle size, and of course they do all these cool things. They segregate very rapidly. One of the things that we're trying to explore from a statistical mechanics dynamics point of view, in appealing to classic statistical mechanics, which we have done for single particle sizes, namely going all the way back to a Boltzmann derivation of the Boltzmann distribution and appealing to the same style of analysis. If we can understand more clearly how different grain sizes, how momentum is partitioned between different grain sizes, I think that if we begin to understand that problem, we will be on our way towards getting at a clear understanding of how we might take a probabilistic formulation and specifically get at the dynamics of the mixed grain problem. I know that Doug Gerolmak currently is beginning to, with viscous flows, look at mixed particle problems, and in fact, my hope is that they will actually begin to think about how the momentum becomes partitioned between the different particle grain sizes, even though it's a viscous flow problem, and it's sort of like Kimberley simulations, in which you're in effect turning off the turbulence and looking at the granular physics part of the problem. Let me just add that Doug would suggest that there's another effect, granular effect, and that is that the granular physics is actually contributing to setting the configuration of the surface particles, and that has an influence. Kimberly probably can speak far better to that point than I can.
Thanos?
Thanos Papanikolaou, University of Tennessee. I had a couple of questions, but just for the sake of time, just I'm going to say an observation. You mentioned about the jamming effects, and that they're non-local, and I totally agree. We've seen the same thing actually happening with flow, uni-sized particles, getting those jamming effects, and to put things into a context with the earlier discussion we had earlier today, actually we see those type of phenomena more during the low relative submergence, which is why I mentioned the transition in the shift that you see in the velocity profile. So some interesting thoughts there. Regarding the question that Gordon raised, actually Doug and we're working together on this. We're looking laminar flow, three levels of gradation or degree of difficulty. One is basically turbulent, then laminar, and then just collisional effects. So it will be interesting to share, results and or ideas.
Be nice to talk to you about it more in the future. Thanks.
I have a question myself, if I can dare. One for both. For Kimberly, I would like to ask, I think it's somehow related to what Bill asked also. The definition of the surface is critical in that it changes the profile in your model. I understand that you consider also moving particle within, you said in the paper is written, the surface defined as the average value of the top of the particles of the bed. Can you specify better? Because which are the particles where you are averaging?
I'm trying to remember. So.
It's written.
Okay. So you want to know how do we specify what the bed surface is?
Yeah.
So we look at the particles that are the topmost particles. So there's some sort of gridding. And then what are the topmost particles in the grid that are moving with less than the way that we define the surface velocity to be for the fluid? So there's the fluid velocity. What are the particles that are moving slower than that? And they're part of the bed. The average of the particles in the surface along the grid.
Okay, thanks. And I have a question for David. My experience doing some experiment with particles is that depending on how you define entrainment and strainment, when a particle is just shaking a bit or moving, you have completely different Hopf lengths and different entrainment functions. I guess the equation do not change, but the distribution do change a lot depending on the definition. I would like a comment on that.
Okay. Let me start off by saying something about the experiments. In the flume, our flow depths are sufficiently large. These are subcritical flows. Our flow depths are sufficiently large that we can place a plexiglass sled on the surface of the water, and the depth is such that the boundary layer that develops beneath the sled doesn't influence the sediment bed directly beneath it. In turn, what that allows us to do is view the bed through the sled, and we don't have any distortion of the images that goes with undulations of the water surface in the absence of a sled, in which case you often will see a particle that's not physically jiggling, but is jiggling because of the effects of refraction associated with the water surface. So first of all, we remove that. Secondly, indeed, we do see particles. Mostly this occurs during entrainment as opposed to just after disentrainment, where the particles simply jiggle in its pocket without moving.
But that's a question. How do you define moving and jiggling?
Yes, okay. All of our particles in all of our experiments so far, we have selected manual tracking. So I want you to imagine taking your mouse and putting it on the centroid of a particle, clicking it, and then doing it 300,000 more times. At sub-pixel resolution, that's important to the definition. We actually watch the particle that jiggles in its pocket without any coming out of the pocket. We do not include those within our description of motion. It has to have, over the full time series, have changed its average position beyond simply jiggling. So we're not working with jiggling particles. They have to have had a net displacement of at least 1 pixel.
I'm saying that because I have the experience then truncating, putting a threshold less than 1 pixel, less than 1/10 of a diameter, less than 1 diameter, and then playing with the threshold. I had a continuous change of the PDF. So there was no reason to put 1/10 of a diameter instead of half a diameter or 1 diameter. We couldn't see any nick point or nothing, saying that there is, in that sense, a difference between jiggling and... I couldn't find an indicator in that sense.
In that regard, a particle, by our definition, a particle in motion is in motion if either it has a streamwise or a cross-stream velocity. One might say, but we're mostly interested in the streamwise velocities. Well, maybe that is correct. But by the definition of probability, the probability of a streamwise velocity of 0 in the presence of a finite cross-stream velocity, well, that probability is identically 0. So these do have streamwise velocities if they are moving. So motion to us is motion regardless of the direction of the motion.
Okay, thanks. I think I've abused a bit of my position, and I also think it's time to close this session. I thank you all, and we go to lunch. Thanks.